the recording. So now the session is being recorded, and the so this session is generally open for all. Okay, this session is generally open for all, and we have this session over GoToWebinar, in which the attendees are unfortunately not able to see each other's questions. But from session 2 onwards, we'll be using something called GoToMeeting, and you'll be able to see each other's answers. And so everyone except myself is muted. You can ask questions by typing in questions window. Instructor can read the questions before answering, and I will read so that the question gets recorded in the video, as well as everybody else knows that what question I'm referring to. To get better answers, keep your messages short and avoid chat language. All right. So this is an open session for all, and so expect a little bit more questions, and feel free to ask as many questions as you want. Okay. All right. So there are going to be close to, in this particular session today, there are going to be more than 30, 40 attendees, maybe more. And in general, our sessions, the usual sessions do not go beyond 24 attendees. All right. So a little bit about No Big Data. So No Big Data is an organization focused on instructor-led trainings, and our very big focus is on expert instructors. Most of the people who will be working as instructor with us are from industry, product development specifically, and we are continuously doing innovation in the field of learning. For example, we have Cloud Labs. Cloud Labs is an online place where all the tools are installed. All you need to do is connect to those machines and then start using them. Then we have learning management system. All the recordings, presentations, assignments, quizzes, and all the project work will be available in that online session, online LMS. So, and the access to LMS will be lifelong. And we provide you a real life project, but real life project is generally provided to those who really perform good in our assignments. And but for all of the people, we provide the project, and we provide a course completion certificate to all. And our course is good for if you want to go for the certification by Hortonworks and Cloudera and other parties also. So our course is compatible with all of that. We provide you 24 by 7 support over email, and in case the issue is not being resolved, we generally do it over the webinar itself. We take the control of your machine, and then we can look at what's going on, or we look at your session on Cloud Labs, that what's wrong with your code or what's wrong with the session. So that is the way we provide support. And also we connect all the No Big Data alumni together, and also we keep on sending you the jobs in case you are interested. And if there are in future there are complimentary sessions, we keep on giving those free sessions to all our um, students. Okay, so overall agenda is to stay connected with our student, and so that is how we have been uh, we have built our organization. All right, a little bit about myself. So before I would love to hear from you. Please introduce yourself in the session over the questions window. It's great if you introduce yourself, a little bit brief background about you and where I located. All right. So please introduce yourself. And here is my introduction. I did my graduation 2002 from IIT Roorkee, and then I joined a company called DE Shaw, where we built big data systems before the term was even coined. Okay, so we were dealing with a terabytes of data at that point of time. We had a cluster of 10,000 nodes using which we churned a lot of data. Then I started a company called Tbits Global, and in that organization, we built document management system for large enterprises. Okay. And afterwards, I worked with Amazon and InMobi and worked on building the high throughput systems on big data. Okay. So that's a little bit about my background. And in 2014, realizing that in the learning area in big data and latest technology, there is a big vacuum, we started this organization. Okay. So that's about me. So let me basically go through your background as well. So we have Ingoba. Ingoba is working with the CSC and currently based out of Miami and is a Java J2E developer. Great. Welcome Ingoba. I'm sure you will like the session. And if there is any questions, feel free to ask. We have Srinivas. Srinivas is a project manager in Washington, D.C. And okay, okay, great, great to know you, Srinivas. All right, and we have we have Dia. Dia is a computer science engineer and is working in Paris, France. Welcome, Dia. And we have Vikas. Vikas is from Austin, Texas. Welcome, Vikas. And Vikas is into is a software developer working in Java enterprise application. Great. Welcome, Vikas. And we have Robert Holder, and he lives in Austin, Texas, and he is doing a web development in Perl and SQL. Great, great, great. We have a great set of. We have Abhishek Parmar, who is pursuing his BTech from VIT. He is still a student in computer science and programming, and he is attending the session. All right. Okay, we have Kirti, and Kirti is from San Jose and working in Sandix Corporation in Dev Test Engineer, have wide variety of experience in QA and automation. Brilliant. Welcome, Kirti, and welcome. All right, we have Sean Dunn, who is from Houston, Texas, and has a background of web design. Great, great. All right, so looks like there are quite a few people. Yeah, Sean is saying go Texas. And we have Nitin. Nitin Patel is a senior software engineer with iGate and working for 5.5 years. Great. And Vikas is working with TK20 Incorporated. Great. And Nitin Patel is from Bloomington. Great. Great to know you, Nitin. And all right, all right. So Dhia is technical architect because we missed that part. So we have Abhishek. Abhishek is working as a senior dev manager in one of the big, one of the high tech companies, and he works in Redwood Shores in California in US. So we have Ling Li. Ling Li is analytics manager at Lbox, JWT and WPP Group. We provide so the company provide marketing service in Unilever, Walmart, and Metal. Great. And we have Ramesh. Ramesh has been working in various analytics space for 15 years and okay, work mostly with Oracle BI stack and currently located in San Diego, San Diego, California. We have Revant working as Java developer in Thomson Reuters in Bangalore. We have Kiran working from Bangalore and working in virtualization and cloud computing. All right, so we have Bhuvneshwar Jaiswal working in Nextify as web developer. Brilliant. We have Amish Shah. Amish is working with Riverbed Technology in the USA in Java and data collection product, where they collect a lot of network data and we use it for analysis and business intelligence. Brilliant. All right, so we have Sandhya, who is an application developer in Houston, Texas, and Revant is, having experience of 4+ years of experience, and we have Anirudh. Anirudh is working as senior software engineer with 13+ years of experience in Java and J2E, and great. And Anirudh is also from Bloomington. So there are two persons from Bloomington actually. And yeah. So yeah, so you can basically, Aruna, you can write in this questions window. Okay. I can read your question. How do I submit? So just write your information in the questions itself. All right. Great. So we have a great set of audience today. Almost everybody is from a great background. And all right, we have Vishnu, who is a software engineer, Pro Web Technologies, Bangalore, and he has worked on various technology. And we have Aruna from Florida, IT consultant, specializing in web technologies. Great. And yes, so Vishnu Raj is interested in. So Vishnu Raj is from Bangalore. All right, great. Now we. Okay, great. So Vishnu Raj is interested in Python and big data. All right, so welcome all, and that was a great set of audience we have, and we'll be going through an interactive session. So feel free to ask questions. I will stop at the end of every slide and answer your questions. Okay. So today's topics are these, and so first and foremost topic is, if you have to answer what is big data in 2 words, what will those 2 words be? What is big data? If you have to answer this question in 2 words, what those 2 words be? Yes, anyone? Nitin says large data. Okay, go ahead. Son says velocity and variety. Ingoba says high data volume. Okay. Anybody else? Aruna says data mining. Okay. Pramesh says complex data. Lingley says 3 V's. Okay, okay. That's like giving a pointer to the whole list of things. Okay. So we have Vikas. Vikas says data analytics. Okay. Robert says terabyte mining. Kiran says large volume of data. All right. All right. Okay. Revant says large data with different structure. Abhishek says data unmanageable by conventional tool. Brilliant. Sandhya says huge data structured and unstructured. Okay. Dia says data science. Okay. Okay. Vishnuraj says that analyzing data gathered from different sources. Brilliant. So we have got a very brilliant set of answers, and this approach of 2 keywords is probably a very good one. And okay, Basant says managing and analyzing huge data. Okay. All right. So okay. Okay. So here there is a very crisp definition we are talking about, and the definition of big data is heavily abused. So I'll try to make it very, very clear. So the kind of data, in very, very simple words, so the usual definition is data of very big size, which you cannot process with the usual tools, and you need a distributed architecture to solve that kind of a data issue. Okay. So if somebody asks me the two keywords that define big data, I will say distributed architecture. Okay, so all the tools in this course which we will deal with, all of those tools are big data are distributed architecture tool, meaning they do not run on one machine, they run on multiple machines simultaneously. Also, we do not transfer data. Instead, we send the code and apply the code on existing data. So that is the biggest difference in the definition what we have been given. So in the whole session from now onwards, we will talk about all the components we talk about. Those components will be of distributed architecture. Okay. Now, what do we mean by distributed architecture? All right. So here you can see that in a distributed architecture, you take your usual computers, connect them together in a network, and write the software such that this all of those computers work together to solve a single problem. All right. So and the other definition which we always confuse distributed with is parallel computing. In parallel computing, you have specialized hardware which has multiple computers, multiple processors, is a single computer having multiple processors and sharing the common RAM. Okay, that's a parallel computing. So the good part about distributed computing is that you do not have to build any specialized hardware. All you need to do is build a specialized software which can work in tandem with other instances of the same software to solve your business problem. Okay, so distributed computing is what the whole big data is about. Meaning all the softwares, whether Hadoop, whether Apache Spark, whether HBase, any soft any tool which we'll study further has to do with distributed computing. Okay, and that's where the difference is lying. Abhishek's question is the distributed computing in big data similar to cloud computing? Very good question. So the answer is no. When we say cloud computing, what does it mean? The cloud computing means computers hosted at someone else's place. It's as simple as that. Cloud computing means computers hosted at somebody else's place. Meaning, you are not keeping your data in computing in your place. Instead, at some safe or secure place, we are putting it. All right. And you don't require a physical access in order to control this computer, turning it on, turning it off, or replicating the computers over to multiple machines. Is all of those things lie under cloud computing. Okay. So, so all of you are clear about these two definition. First is distributed computing, parallel computing, and third is your cloud computing. Okay, cloud computing is as simple as instead of running program locally, you are running program on a computer hosted at somebody else's place. Okay, that's what is known as cloud computing. Okay, I will try my best to oversimplify things, okay, in order to be very clear in what I say. Okay, so if there are ifs and buts, you will have to get into a little bit more details. Okay, if there are doubts, ask the questions. So these are the two things. And yes, Abhishek, I think I should add one more screen here saying cloud computing. All right, great. So when then comes like we talked about structured and unstructured data. That is something people need to understand, because most of our existing databases. So when we say, again, I'm going back to my first slide, data of very big size that cannot be processed using usual tools, and we require distributed architecture to solve that kind of problem, then we call that we are dealing with big data. Okay. Now, this kind of problem might arise because your data may be unstructured or your data may be structured. So the definition of structured and unstructured data is, structured data means you know clearly that what are the fields in the input data and what are their data types. Then when you know very clearly, for example, a table in your database, you do not have to do processing of the data in the table just to figure out the data type of various columns. This is structured data. Now, what is semi-structured data? Semi-structured data is the data in which we know the fields in the input, but we do not know their data types. For example, data in comma separate files. And third one is unstructured data. The unstructured data could be something like a video where the whole of the data is in the form of binary, or the unstructured data could be the logs generated by your devices, where in such a data we do not know the input fields, neither we know the fields in the input, nor we know the data types of the fields. Okay, and therefore we call such a data unstructured data. All right, any questions still here? Now this is the general definition of the way IBM has defined the big data. So okay, but important part is that when we say that our usual computers cannot handle and we need a better solution, then what is it that makes it unhandleable? First is volume, second is velocity, third is variety. So these are the various properties of any data that might push you towards a situation where you realize that our existing solutions are not really capable of solving your problem, right? So the first characteristic of the data is volume. When you are having a humongously stored data already, say for example, in the you have to store, or you already have data stored at Facebook, say your photos, your videos, everything that's stored at Facebook, that's a volume of the data, the volume that's stored at Facebook. Okay. Now similar to that, there could be many kind of databases. I'm just taking Facebook as an example. And next is the velocity. Every time you log in into Facebook, you ask Facebook about your feed. And so which means everybody across the globe is asking Facebook every millisecond, okay, every say half a second, for the feed on their mobile phone, on their desktop, on their laptop, everywhere. Which means there are millions of requests per second. There are millions of requests are going to Facebook per second. Okay, so this is called velocity. So either your problem might be related to too much of data to store, or too much of data which is stored and you have to process that, or there is too many requests, the data flow is too high that a single computer cannot handle, and you need multiple computers to even respond to the simple requests. Third one is variety. The variety, when we say variety of the data, it also means the complexity of your problem. Okay. It also means the complexity of your problem. For example, so let's say that you have Google Maps, or you have any maps. Even though the data may be small and the velocity may be very small, but still churning a map might take a lot of time to basically just to find a path from one location to another location. You have got a Google Maps, for example, and you have to find location from one point to another just in a single country. For a country, the Google Maps might be, say, 50 GB data, but finding a path in Google Map from one point to another is actually a very complex task. Okay, so variety may be of two reasons. When we talk about the complexity arising in computing, it may be because of two reasons. One is because of the way the data has been kept, and second would be the kind of need you have. Okay, for example, you have to automatically organize the data into clusters. Okay, so that's a very complex process. That's a complex process, and because of that, you will realize that if you do it even on the supercomputer, it might take few weeks to solve your problem. Okay, that's when you say that our problem cannot be solved by a single computer, and then you move on to distributed computing. Okay, fourth is veracity. Veracity is kind of a quality which has been unnecessarily forced into the definition. Veracity means the data due to confusion. And though it's a very common problem in most of the organizations, that for the same problem, the same data set has at least 10-15 copies. Imagine you asked for temperature data from various people, and various vendors gave you the temperature data in various different formats. One gave you the temperature for each zip code, other gave you the temperature, global temperature of global weather condition temperature. It gave you based on one gave you based on zip code, other gave you based on GPS location, other one gave you based on station ID, which might be multiple in each zip code. Now, this way, if you ask for the data from different vendors, or if you look around in your organization, you might get multiple set of data for the same question, right? Same requirement, you might get multiple set of data. And because of this kind of now, when you get this kind of data, you are not sure whether to keep dataset A or dataset B. So you end up keeping all the datasets until you decide that this data is the only one which is the source of truth, and rest of the data can be deleted. But till the point you take the decision whether to keep one dataset or the other, till that point you will have to manage the whole dataset, and that is what will lead to the volume, and hence the veracity, the doubt, the confusion leads to the volume, and hence it leads to the big data problem. All right, so okay, so Dia's question is complexity not the velocity? No, complexity is based on the kind of data you already have, the stationary data you already have, and you want to solve that. Okay. So while in velocity you have too many requests to handle, and the functioning of the way we design the tools to handle the velocity, they basically are very different from the usual stationary tools. But in all of these kind of tools to handle all these velocity, volume, variety, the single thing that is common is distributed computing. Okay, so Dia was able to answer your question. All right, we have Indy. Hi, Indy, and feel free to ask your question. Nitin is saying that volume example would be size of 10 billion photos on Facebook. You can see that Facebook is, I've already mentioned, 500 terabyte of data per day. All right. Yes, go ahead, Indy, ask your question. All right, great. Moving on, and feel free to ask your question. At the end of slide, I will take up your questions. Okay. Okay, quick question. How many bytes are there in 1 petabyte? Okay. As soon as I get a correct answer, I will move. So we all talk about, whenever we talk about big data, we start with megabyte, gigabyte, and then terabyte, petabyte. So what do you mean by a petabyte? How many zeros are there? Great, great, great. So I've got many correct answers. Yes. So it's 10 to the power 15. Yes. So it has got 15 zeros. Okay. It has got 15 zeros, and that's too much of data if you think about. All right. The general way to remember the data set is using this table. You start with kilo. 1 kilobyte is 1024 bytes, and a byte is 8 bit, which means a single byte can store around 256 states, and a megabyte is 1024 kilobyte, and so on. Okay. So kilo, mega, giga, tera, peta, exa, and zeta, iota. All right. That's how you can remember. All right. So we talked about two things. First was big data, meaning big data, we gave a very crisp definition. The kind of problem you have if you require a distributed computing, we call our data as big data. And petabyte means 10 to the power 15 bytes. Now you are given 1 petabyte of big data. Now what you need to do is, when we say 1 petabyte is a big data, you might revert and say that what do you want to do with 1 petabyte data? Okay, so let me say that we just want to do a very basic thing. Every day we want to count how many vowels are there in our 1 petabyte data. How many vowels are there in 1 petabyte? That's all we want to do. Okay, so do you think for that kind of work, every day we want to do, in 24 hours we want to do, we count vowels in our 1 petabyte data every day. So do you think, based on this requirement, 1 petabyte is a big data? Yes or no? Yeah. Robert says no, while Sean, Ingoba, and Ramesh, Aruna, Pooja, Abhishek, all of them say yes. All right, Dia, Vikas, everybody says yes. So yes. So Robert, so give me a reasoning. Yeah. So the problem with 1 petabyte data is, even if you do a very simple processing, it is going to take a lot of time. And why is it so? Okay. The reason is, okay, so let me say that. So since 1 petabyte is a huge data, and this particular question will answer you. So if you have 1 petabyte data and there is one hard disk, and if you're trying to read 1 terabyte data using this hard disk, do you think, how much time do you think it is going to take? 1 terabyte data, not petabyte. Anybody? If it's our normal hard disk, okay, normal hard drive. So how much time does it take to just read 1 terabyte from this hard disk? No processing, just reading. Right. So the general perception is that it does not take much time. The truth is it takes around 6 hours. Now, if you have 1 petabyte data, it will take 6,000 hours to read 1 petabyte of data. Okay. You will need around 6,000 hours to just read the data from the disk. Okay. Now, without involving a distributed computing, without using multitude of computers, you cannot really solve the problem of reading 1 petabyte data every day, because reading 1 petabyte data using a single computer is going to take 6,000 hours, and we said we needed 24 hours, right? Therefore, yeah. So Dia's question point is that it depends on the CPU. No, it does not depend on the CPU. Even if CPU, when we read the data from the drive, the CPU is going to be idle. Okay, CPU, RAM, nothing will be used. It's only the disk which is going to take this much of time, because the disk has its time, it takes some time to read the data. All right. Okay. So that is the reasoning. So Robert says that I changed my grade. So I'm able to convince Robert that 1 petabyte data is a big data. All right. Now, so that's the thing. So whenever we are given a problem, we have to figure out, we have to do a back of the envelope calculation and figure out that how much time does it take even a supercomputer to solve this problem. And please note that even if we had supercomputer and we are reading 1 terabyte data using supercomputer, it will still take 6 hours. It might take 5.5 hours for a supercomputer because they might have higher RPM drives, but it will not take, minutes. It will always be in hours, no matter which supercomputer do you use. Okay, so it's not about, when we deal with a humongous data, when we deal with big data, it's not really about the processor or the CPU. It's more about there are the all components. We'll talk about all the components. Why do we need big data? Okay, we'll talk about more. So this is a traditional diagram which shows that in 2007 2002 the data started exploding really high, meaning digital data, not the analog data. Analog data is growing lower. Analog means the data which is printed data, the books, everything else. So that's on the shrinking side, while everything is getting converted into digital storage, and there's a lot of data generation happening. Now, the reasoning why in 2002 the data started exploding so high. These are the two reasons. On the left hand side, you have smartphone. On the right hand side, you have connectivity. On when we talk about the computing, when we so on one hand, the hardware became smaller, faster, and cheaper. Cheaper, faster, smaller, or and on the other hand, the connectivity became more and more omnipresent. Meaning, you have got smartphones which are really cheap and faster and smaller, and those smartphones are very well connected all the time. So while these smartphones act like a data generation agent, they have cameras, they have all sensors, there are lots of component inside devices. Okay, so when we say smartphone, you can say that these smart devices, the devices have become smaller and faster and cheaper, which means everywhere they are available at a very low cost, and the data they generate is being multiplied due to connectivity. For example, as I'm giving this webinar, it's being delivered to 50 people, and by the end of 3 hours I'll be upload this would upload around 5 to 6 gigabyte of data, or maybe 1 to 3 gigabyte of data. I don't know. So assume that it'll upload around 2 gigabyte of data by the end of this session, and this 2 gigabyte would become 100 gigabyte of data transfer from the GoToMeeting server to you, which means the connectivity, as usual, in duplicates the data. Connectivity makes the data available everywhere, and hence combination of the hardware and the connectivity had made the data availability everywhere, and has multiplied the data generation. Okay, on top of it, when the hardware and everything has become so available, software inevitably had to come, and there are some billion software as of today, like Facebook, Twitter, and everything, so that we have lots of data of the globe. All right. Aruna's question is, what about solid state drive? Yes, solid state drives are real little faster. Solid state drives. So the her Aruna's question is related to the previous slide when we were talking hard drives. So solid state drives are around 10x faster, but still they do not solve too much of problem. Okay. So and we will see that you will understand why the solid state drive still does not solve the problem of volume. All right. Amish's question is, sorry for going to question 4 V's for big data. Does all 4 V have to be present to be big data? No. Those 4 V's I talked about, volume, velocity, variety, and the fourth one was veracity. Any of those 4 V's might make your data big data, because any of those characteristics or a combination of more than one characteristics make your problem complex, and hence you might require distributed computing, and you can start calling your data as big data. All right. So Lingley saying that the sound is not there. Is sound there for everyone? Okay. Okay. Great. All right. It's back now. All right. So Amish, I was able to answer your question. All right. All right. Great. Moving on. So okay. So question to all of you. Which components impact the speed of computing out of these? CPU, memory is read speed, the rate at which CPU can read from the RAM. When I say RAM memory, it means RAM, random access memory. Disk speed, disk size, network speed, and all of the above. Great. So everybody has understood this part, that it's all of the, I'm pretty happy to hear this. Okay. So great. All above the above. Okay. Great, great. I've got a great set of audience. All right, so now when we talk about computing, so we have already answered the question, so you are well aware of these components. So whenever we talk about computing, it involves multiple components. The impression which Intel and these processor companies have made is that it's only the CPU which matters, right? We all have developed this impression that it's the CPU, that's the only thing that matters. When we try to buy a laptop, the only thing which we consider is the CPU. Okay, but the truth is, CPU is the main component which is mostly free. Okay, so if you observe your CPU of your computer, all the time it will be less than 5 to 10% utilized. Okay, so CPU is rarely the bottleneck in the computing. And when you are doing a computing, when you are doing a usual computing, and the things which actually delay, the things which actually give you an impression of delay are something different. First one is the rate at which you can read the data from the disk. Second is if your program is reading from the network. Okay, and after that is your RAM. Okay, if your RAM is smaller, then more data will be on the disk, and hence your computer will be slower. Okay, while the CPU comes at the last when we think about the computing. Okay, although there are some problems which involve more CPU, but those problems are generally rare. Okay, and also whenever you have the CPU bottleneck, a general signal to the developer is that you need to solve you need to come up with a better algorithm. If your CPU is going 100%, if your CPU is going to 100%, that generally means that your computer is doing something really wrong. Okay, although this statement is not true 100% all the time, but that's a general the case. If you have written a while loop, which is infinite while loop, whether you have got i3, i7, or Intel processor, AMD Core 2 do whatever processor do you have, all of them will go to 100% CPU usage. Okay, it will never be that one processor will be on 50% CPU, another will be 100%. So okay, so the only point I'm trying to derive here is that CPU is not the only component that matter, it's these other components. Okay, so and these components work in a very good fashion. Storage, all these components like number 2, 3, and 4 acts like a storage. So when your RAM is, when your data is too big to churn and it's not fitting into RAM, you start pushing it to the disk. And when the data is not fitting into disk of a single computer, you start pushing it into the network. Therefore, all these components work closely with each other. And when we talk about big data, at least one of these are going to become bottleneck. Okay, Vikas's question is good. He says that how does disk size become the bottleneck? Disk size impact the speed of overall. So if your data is not able to fit into disk size, what will you do? You will put it on network, right? Or if you had, let's say, and therefore the disk size is actually moving the data to the network and hence impacting your overall speed of computing. Correct? So in that way, these all components matter a lot when it comes to the computing. All right? So if you have a smaller RAM, the RAM size, then you have to push more data into the disk and hence slow speed. If you have more smaller disk, then you have to push the data to the network, hence slower speed and so on. Okay, and these kind of problems are solved by these new generation of components by using distributed computing. All right. Now, Abhishek's question is, does network also create big data problem? Of course. So when we are having our data spread across network, and this data is huge, right? This data is huge. If you try to transfer big data over the network, it is going to it is never going to work. Instead, you always transfer the program to the data instead of transferring data to the program. Okay, the way we had always thought about that, we will have this query which will run on the data and we'll have this data coming back from here to there. Okay, so always the intention in is to send the code rather than data. Okay, because network becomes a bottleneck for big data. All right. All right, so these are few example big data customers. First is, although there are lots and lots of use case, these are few use cases. Those gave a better result for the industry in the beginning. Now there are many use cases everywhere. These are the initial use cases which impressed a lot of industry pioneers. All right. So we have recommendation engine, search quality. So a recommendation engine is something that gives you a recommendation. Okay, so like in case of Amazon, they are showing you that people who bought this also bought that. Okay, while in the second one there's a curated recommendation saying you can wear this particular cloth with these things, right? You can wear these clothes with these shoes and other parts, right? So on the right hand side, it's a humanly created recommendation. So, and on the left hand side, it shows that customers who bought this also bought this. So it tells you that it is based on data, right? And therefore, while on the right hand side, you will always think that this may be biased. You always think that this may be biased. Maybe some people just sat down there and put these things so that we can buy these costly stuff and make money for them. And while on the left hand side, it is done based on the data. Okay. And therefore, the intention of the end user would be to trust the left hand side recommendation more. And because of this, Amazon actually makes a lot of sales based on recommendation which are sent as email or shown on the website. Okay. And this kind of recommendation is not very difficult to generate. The other kind of recommendation is that based on the movies you have rated so far, showing you the proper movie recommendations as done by IMDb and Netflix. So based on various kinds of ratings you have given. So Nitin Patel's point is network, think of bandwidth. Yes, that's a correct way of thinking. Whenever we think about network, we should think about bandwidth. Now, so Pooja's question is the big data problem are concerned only with the speed with which we handle it, not only with the speed which we handle it, but also how long does it take to solve your problems? Are those times acceptable to you? Okay, theoretically every problem can be solved, but question is how much time will it take? Will it take a million years? Will it take 1,000 years? Will it take a minute, or will it take a second? Okay, so whenever we are solving a problem, so with respect to computer, it's generally about the time. How much time does it take? So Ingoba's question is, which means keep data wherever it is, just communicate through software, right? So we'll discuss these things in detail more, that how to store the data in order to process it in the network using in a distributed computing. All right, you'll understand that part. Okay, but this kind of impression is okay right now. All right. Now, the recommendation, the kind of problem which we will discuss further in session number 8 is how do people generate the recommendation? They basically use the existing algorithm to generate the recommendation, and one of the pretty good algorithms are from Apache Mahout. Basically, Apache Mahout asks you for three things. Okay, three things are user ID, who rated which movie, how much, and it will give you the recommendation. And this example will take. So this is how we generally generate the recommendation. And Mahat works on the whole Hadoop stack to generate these recommendations based on the input data. So these are the only three columns data that is input to Mahat, and based on this three column data, Mahat will generate recommendation for you. This is how people generally do that. Basically, the way recommendations are generally generated is we cluster the user together, we find out who is similar to who, and then we start giving recommendation, we cross recommendation to each other. All right, so that's how we generally do it. We'll understand it later on, but recommendation and the sentiment analysis are the two problems. Those were the first solved for the big data problems, for the big data use cases. And sentiment analysis means what is the general sentiment of the people towards your product or your brand. Okay, so generally the way, as of today, before the In 1990s, what people used to do is, if there's a new movie release happening, they will go to the theater, wait for people to come out, ask their opinions, and then, based on a small sample set, they will publish in the newspaper an article saying this movie is going good or going bad. Okay, but today the way it's done is different. Today we listen to the public channels such as Twitter, so and understand how is the general sentiment of the people towards us. Are people using negative words against our brand, or are people using positive words? Are Is their sentence negative or positive? And there's a lot of research that has gone into sentiment analysis in understanding people's sentiments. Okay, so the way we generally plot a sentiment analysis is, on the x-axis we put the we put the timeline. On y-axis we put the total number of positive and negative sentiment against our brand. All right. The other use cases other than this, I'm going back to the previous slides, this one. The other use cases other than recommendation engine and sentiment analysis are A/B testing and search quality. So whenever, even if your data is small, say for example 50 GB of data is there, and what you need to give is, you need to give a brilliant search solution to your end user, right? And to give a brilliant solution, you need to actually do a lot of hard work. Okay, and such as, say for example, when the user searches for something, user say searches for blue space dart, right? Now, whether users BLUE uh, DART, whether user types blue dart this way, or whether user types as BLUE space DART. So there are hundreds of possibilities of typing blue dart. Now, the user expects that they should get results even if they type a wrong word. And there could be the other names with which blue dart is known as, and therefore user expects you to give the results. Okay, and therefore you need to build a brilliant dictionary of such kind of aliases. Although there are very brilliant dictionaries available as of now in the public domains, which you can use as the search keyword correction, and use that in tandem with your existing solution. But every time you improve the search quality, every time you try to improve search quality, you will find that you need to churn a lot of data, and therefore most of the search quality issues are big data related. Similarly, A/B testing, you have got a website which is being hit by millions of users, and you want to analyze that what feature is working better. Okay, what does it mean by A/B testing? A/B testing means, say you have a medication and you wanted to test over some people whether a particular medication works or not. So you generally take you basically take 100 people into this study. Uh, Out of 100 people, you basically, for 50 people you give the medication, and for rest of the 50 people you give a pacifier, although all of them believe that they have been given medicine. And then you see the side effect, and you see observe whether this particular medicine solved but the disease or not, cure the disease or not. So in the similar way we also do the A/B testing on the websites. So whenever we want to change a particular feature, let's say you want to change the header of your website. Okay, you want to change it from blue to yellow. And so what will you do is you will basically, you for 50% of the user you will say one kind of header, and for 50% you will show the existing one. Okay, now current one was black and you wanted to move to blue, so for 50% user you show the blue one, and then observe and then observe how did how much average time did the user stay. If users are staying lesser number of time in case of a new background, new header, that means your website, your header is bad. Okay, so this way you generally decide on on whether to keep this color or that color, whether to introduce this feature or not, just based on users data. And these kind of problems are really huge. So in case of Amazon, I when I worked at Amazon, I was handling the retail page as in the page from where most of the purchases happen. There, every feature was running at least 5 variations. Now you can multiply that and you can compute how many variations are there for a single page. If there are 50 feature, each feature is having 5 variation. Okay, so the total number of variation of the page are really huge, and that's where the complexity of A/B testing starts. Okay, so I'm not on recommendation slide. Is my recommendation slide still on the screen? We are on the example big data customer slide. Okay, okay. So something wrong with Vikas's, connection. All right. So, all right. So there's A/B testing is one such case. Then customer churn prevention, avoiding customers leaving you. Network telecommunications are using big data to a very large extent because their data is pretty huge anyway. All right. And then there is a government that is using it for fraud detection. And basically, these are big data tools. When we talk about the big data customers, it's basically whether they are using big data tools or not. Okay. It's not a single set of data which these people are customer. And then the healthcare and life sciences. Probably every problem, just like telecommunication, every problem which healthcare and life sciences face has to do with big data because their data is really huge. Okay. Now, Pooja's question is that could you tell how Mahat recommends movies the users might have rated for other different movies? Does the algorithm look into genres of the movies rated by the users and then recommend? Right now, in this case, the example I gave uses a very trivial algorithm whereby it does not look at the genres. All it looks for the user similarity index. Me and you, are we similar to each other in, are we similar more than how different are we? So let's say me and you have watched 10 movies each, okay? And we both like, say, 6 movies, same 6 movies to the similar extent, which means, which means out of total movies, so 10 yours, 10 mine, and 6 are common, which means 20 minus 6, which is total 14 movies. We are similar by 6 by 14. So this is a similarity index. So this kind of thing, basically it computes this kind of similarity index between all combinations of users, and then it gives the recommendation based on the most similar users to each other. Okay. And that's how it works if you do not give genres. But there are other techniques, other algorithms provided by Mahat, which also asks for genres, which not only takes into consideration the movies rated, but also the attributes of movies. Okay, did it make sense to you, Pooja? All right, these are other people who have been using big data for quite some time, but this is a old slide. Now, there are many myths which are going around and which have been going around for quite some time. And one of the most common one is it always means data beyond few terabytes. Okay, that's not true because if you have to find recommendation in 100 gigabyte of data, finding all permutations of users takes a lot of time. And therefore, even if your data is in hundreds of gigabytes, it's not solvable by a single computer, and hence you require big data. So as we gave an example of variety when we were talking about Google Maps, so it was apparent that the big data has nothing to do with directly with the volume of data. Okay, but generally the data below 1 gigabyte data, you can most of the complex algorithms you can run on those. Okay. Yes, Kirti, we are going to share this. And since you are already, so Kirti's question is, are you going to share the slides to us later? So these are already shared to you, Kirti. If you log in into my courses, you will see, because you are already a student, right? So you will see these all slides on the website. Okay. In the LMS, you will see all of that. All right. Now, the next myth is always about social media does not apply to me. That's not the case, as I talked about the search quality and other examples. Will replace enterprise data warehouse. This is another myth. The thing is, most of the tools as of today are not able to give you, most of the big data tools are not able to give you the the transaction kind of capability. And we will, when we discuss NoSQL, we'll discuss that why most of the big data tools, most of the big data databases are not able to promise the great transactions, or they are not able to process the relational properties of the data. Therefore, most of the big data tools as of today will not be able to replace your relational databases. They will exist in conjunction. All right, so they will not replace. It is just a buzzword, no practical application. So that's definitely not true, because I have seen lots of use cases so far, and probably wherever there was a earlier, people were thinking that storing data is a futile act, and people had the tendency to delete a lot of data and thinking that it's bogus. But as of today, when people have realized that they have the ability to handle such amount of data, they are able to derive a lot of insights into data. For example, the recommendation engine which we built for 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 InMobi was based on the Apache logs that were generated by their web server, and that was very accurate. And is a new concept or will be the future? No, it is the same concept which has been going on for quite some time. Some people like D. Shaw and others realized this aspect quite early and had researched a lot into handling terabytes and petabytes of data. And these solutions were their in-house solutions, but they were not shared with the public. But today we have lots of tools which are available in public. Okay, and therefore it's now available to all the people. So although it's made available now, but it has been there for quite some time. Is it expensive? No. Most of the tools are built around the idea that your usual computers can be utilized. Okay. Same is the question when we say read that other myth. We have enough hardware, we don't need more. So the whole premise of all the big data solutions is that they should they should be able to use the software on the usual computers, on the normal computers, not very high-end ones, and is only for data scientists or is a magic. So most of the work that data scientists do or have done, those algorithms are available for everyone to use, so they don't have to reinvent any of that. And thanks to today's open world, most of the the most costly algorithms are actually available in public. Okay, we will build it when we need it. So the my answer to this myth is, when you need it, you won't have the big data, and then you will regret. And therefore, you should. Most of the organizations which I give the advice to is, I tell them to build the capability to store a lot of data, so that once you have data, you can come up with many kind of use cases, and rather than the other approach that when we need it, we'll build it. All right. Also, big data is about Hadoop. No, there are multiple solutions to big data. It just so happens that Hadoop is an ecosystem containing more than one solution. All right. These are the salary trends. You can see that Hadoop is still at the highest high. Hadoop developers are highest paid amongst other developers. And these are fairly new trends. These are of April 2015. Okay. Okay. So the other big data solutions which lots of people ask is, um, related to the other solutions are, first is Hadoop. The other solutions are Spark, Cassandra, MongoDB, and Google Compute Engine. While Spark is just a computing engine, it does not have storage, it doesn't have a database. While Cassandra and MongoDB are great for storing data, but are not great for computing. They don't have great set of libraries. And if you try to use Spark in conjunction with Cassandra, the answer would be that the Spark will try to transfer data from Cassandra, and therefore transfer will eat up all of your time. Therefore, Therefore, almost if you compare the whole stacks as of today, you'll find that Hadoop stack is the most reliable and the most popular one, to an extent that Spark itself runs blazingly fast on top of HDFS. On top of Yarn, on top of Hadoop, it runs really, really great. So your best use cases of today would be either Apache Hadoop, or use the third-party solution like Google Compute Engine. Out of all the solutions which I have compared so far, Google's Compute Engine seems to be really good. Okay, and that's why I've mentioned it. I've even compared the Microsoft Azure. Uh, it sounds really expensive when I looked at my numbers. It looked really expensive, and therefore I've not listed it here. Any big data solutions provided by IBM. IBM does provide some solutions, but those are either very costly or are basically, they have Hadoop's implementation over there. IBM is shipping their own Hadoop's implementation. So whatever you read about Hadoop will also be applicable over there. Okay. So Hadoop is a common open source one. And these companies like Cloudera, Hortonworks, and IBM and Mapr and Qbol, they have derived their, their solutions, and they are packaging Hadoop along with their usual solutions, the BI tool and other tools. But the Hadoop remains common in all those solutions. All right. So here is what we want to discuss about Apache Hadoop. Do you have any questions before we move forward? Redis, yes. So Redis is an in-memory solution, Lingley. And so basically, any data that can fit into memory of one computers or multiple computers together, you can use Redis along with that. All right. Ingoba is saying that are you saying that Google Engine is better than Hadoop? So Google Engine is better in the sense that you don't have to set up anything. Okay, but Google Engine is not really great when you want to do a lot of processing, a lot of data generation. Meaning, if you have 10 web servers running and you have to basically gather all of that data and do some churning. Okay. So, and also if you are hosting your own data center, that might be little less costly, but after some time, not in the beginning days. All right. So the good part is Google is trying to now go with the Hadoop's route. For example, to store the data in Bigtable by Google, now they are accepting Hadoop's API, HBase API. So if you have built your solutions on top of HBase, which is Hadoop's component, you can use the same API, same everything same on on Google's compute engine. Okay, so basically Google is trying its best to be compatible with Hadoop, and therefore it might be a good bet for you for the initial days. Okay, but this is very much up to an organization. Okay, I would still put my bet on Hadoop over Google Compute Engine, because Google Compute Engine gives you gives you only few things, not many things. Okay, therefore therefore you are limited by what Google can provide. Okay, all right, so we have Aruna's question, and this is a brilliant question. The recommendations provided for Amazon, how do we know if they are accurate? Okay, so this is a good question, and my question to you is, if there is a palmist who comes around. Palmist is somebody who's a future teller. So a future teller comes around and he claims that he can tell your future, right? How do you validate that person? You ask him about the past, right? Similarly, the way we build. Oh, the audio is breaking. Still, is it breaking now, or is it okay now? Oh, okay. It's all right. Yeah, I had disconnected the headphone. Is it okay now? I don't think so. Good. So now it is okay. So let me repeat about Redis part. All right. So I was trying to answer the question asked by Lingley. So the question was that what about Redis? Although Redis is claimed to be a big data solution, but it all depends on what we are trying to do. If you have to do a lot of complex in-memory processing, okay, meaning you are handling relatively small data, say 1 terabyte of data, and or maybe say 500 gigabytes of data, and all of that data you want in the memory so that you can quickly process it. So Redis is good in those cases. Also, this data is not changing too often. Okay, so you don't need to read it again and again. So in all those cases, Redis is good. Okay, but we We do not say Redis as the only solution. And I have not mentioned there are many, many tools, many other tools to handle big data. I have not mentioned those, right? So, Lingli, were you able to hear this time? All right. So, any other question before we get into Hadoop discussion? All right. So, dog cutting and Mike Caffarella, I'll just convert the whole points into story. So dog cutting and Mike Caffarella, they were working at Yahoo and they were planning to build a nuts a search engine similar to Google. At that point, they realized that it's impossible to store the kind of data we have from World Wide Web using any of the databases. So they got stuck at that point. And luckily, at the same time, Google made their papers public. Okay, the designs of their internal tools they made public, and these there were three papers. First one was Google MapReduce. First one was Google File System, which detailed how to build a very large scale file system. Second one was Google MapReduce, okay, which told how to build a compute engine on top of multiple computers simultaneously. Third one was a Google Big Table, which means a database, how to build a database on top of multitude of computers. So these three papers became the baseline for dog cutting and Mike Caffarella, and they implemented all these three tools and made it open source, and that's what became Hadoop. Afterwards, afterwards, they included other components as well, and all the components that lie under the umbrella of Hadoop, all of those components share these three properties. First is they have to be reliable, they have to be scalable, and they have to be distributed. Okay, all the components that lie under the umbrella of Hadoop, it all started with those three components. And now, as of today, we have 10 to 12 components under the umbrella of Hadoop. And all of these components are for reliable computing, meaning if few computers go down on network, if few computers go out of the network, still we should be able to get our work done. That is reliable. Second is scalable, which means today your problem includes 1 terabyte data, which means few, maybe say 10 computers. Tomorrow, you need 10 more computers. You should be able to scale out, scale out as in add more computers easily without having to uh, without having to go through too much of hassle. So all of the components should support addition of new computers to the network very easily. Okay, all of them have to have that capability. Third one was for the distributed computing, which means we should be able to distribute the program across multiple computer and get it executed. All right. Now, all of the components that lie under Hadoop and Hadoop itself, all those. So Google File System became Hadoop Distributed File System. Google MapReduce became Hadoop MapReduce, and Google Big Table became HBase. Okay, so they started with these three components, and now there are multiple components, and all of these components are under the open source license of Apache. And probably this licensing is one thing which has changed the way the world works. Okay, now, because of this licensing, people are adopting the component. The good part about Apache license is that you can use it howsoever you want. If you want to bundle Apache component inside your own component and want to sell that component, Apache is completely okay with that. If you want to alter it and use it, then also Apache is okay with that. And similarly, there are there is no restriction whether you want to use it for education or you want to use it for banking. They don't put any such restriction, and that is why Apache license has been such a boon for the world, and that is why people adopted and accepted Hadoop. Okay, so basically, and that is why the Cloudera, Hortonworks, and everybody is able to bundle Hadoop and is able to give support around Hadoop. All right. If you want to also build a company around Hadoop, you can do that. A question is from Vinod. Why should we prefer Hadoop over other? Do you mean that why should we prefer Cloudera over Hortonworks or something like that? Or which one, Vinod? All right, great, great. So it's already answered as per Vinod. So this is what is Hadoop, and we will take a break of 10 minutes and we will come back at in after 10 minutes, which is 10:11 p.m. for me. Okay. All right, so should we start now? It's already 10:11. Okay, should we start now? Great. So before the break, we had a question from Dia. Which are the concurrent frameworks of Hadoop? Probably you are asking about who else is the competitor to Hadoop. So there are two ways to look at. I'll answer both the question. First, would might be that what are the other implementations of Hadoop? So basically, there are Hortonworks, there are Azure, there are Cloudera, and there are MapR, there are Kubel. There are multiple concurrent frameworks of Hadoop. Okay, and if we are asking about whether who else is a competitor to Hadoop, so there are other competitors, say Cassandra, for example. So in Cassandra, you can basically store some data and also try to do MapReduce on top of Cassandra. Okay, but Cassandra is not, though they look like a competitor. For some problem, you might just like to go with Cassandra or MongoDB or other similar solutions like Redis and few more. But a proper competitor providing a similar set of components is not there as of today. Okay, there is not a great competitor to HDFS as of now. And thank you, Vinod. I'm happy that you finding the session great. And Pooja's question is just a general question. If any software is built by a company as open source, if a solution is built as open source, then how do the company benefit from it? So there are multiple models of operations. One is providing the support. So the way most of the open source world works is that open source software is available for free to everybody, and that acts like a marketing machines to for almost every component. So the basic components is free for all. Okay. The only thing the company charges you is for additional support you ask them. Okay. So most of the organizations, large organizations, they don't take things for free. Why? Because they want complete support and therefore they buy a premium edition. And that is how almost every data oriented company works. Yes, thank you, San. So similar to Red Hat. Okay. So any platform or any large software which basically logs people's data, as in which people put a lot of data and the reliability is required, they have to be open source. Otherwise, what if this company goes out of business tomorrow? What will happen to people's data? All right. So that is the reason why you will see almost every NoSQL is open source. Okay. All right. All right, so let's talk about various components that are part of Hadoop. The first one is here, the Hadoop distributed file system, and then there are other components. Okay, so before going to other components, I want to do a deep dive because we have time today. We have still around 1 hour, more than 1 hour, so we can actually go into the details of HDFS. All right. So let me just open that slides. So feel free to ask as many as questions possible. So, all right. So before going into the other components, I would like to deep dive into Hadoop distributed file system. Okay. So Hadoop distributed file system is the component in which the whole ecosystem of Hadoop depends, and we will talk about other components as soon as we finish Hadoop file system. Okay, and feel free to ask as many as questions possible, because there is no problem at all. Even if you feel that question is out of context or question is something which is not relevant, still feel free to ask. It will be up to me whether to answer now or in the email. All right, great, great. All right, so now before I start describing what is HDFS, the architecture, a better way would be to build it from the video. Okay, so now question to you is, if you have 100 terabyte of data, how are you going to store it? Okay, think about it. Now let me go into further details. Imagine you are living in a society, or in a hostel or in a college, and you have got 100 terabytes of movies, all of you and your friends. So you decide that you will build this network where you will store 100 terabyte of data. Okay, and storing it on the cloud or buying the cloud is not really a solution right now, because I mean, if that was the case, then why would we even study what we are studying right now? All right, so how would you store 100 terabyte of data? As simple as that. 100 terabyte of movies, how would you store? Sean says NAS, which is network attached storage. Good, good. In multiple systems, that's Pramesh. Diya is saying store it in many hard disks. Good. Revan says in external hard disk. Good, good. So now this is what we traditionally did. Okay. We generally, what we did was we took a lot of hard disks, put those hard disks into computers, and connected those computers in the network. Now, after we have connected the network, these computers in the network, we mounted or we mapped the network drives into a central folder and informed everybody that this is where you will find these folders, and you can put the movies, and or you can read the movies from this. Now, at the end of day, this is what you get. This is what you get. You get one folder. First folder representing drive 1, second folder representing drive 2, third folder representing drive 3, and so on. When you write something in drive 1, it goes into that particular hard disk in the network, and then it starts writing into that. So, okay. So, Pramesh, so here if you see that it's not possible to attach lot of many hard disk into a single computer. So, so that is why we are building a network right now. Okay. So his question is, advantages of multiple systems will be fetching data will be faster. Definitely true. Just that in our case, it's a compulsion to use multiple machines, because 100 terabyte data, if you have to store, you cannot buy a 100 terabyte disk. The best hard disk as of now are available 4 TB. Okay, and if you have so if you buy 1 TB hard disk, then there are going to be 100 hard drives, and you cannot connect 100 drives to a single machine. So you can connect up to 5 to 6 hard disks, or maybe 10 hard disks into up in a system. All right. So this diagram is clear. So whatever Son you have told, this is how we did, right? Network attached storage. And Adhiya, this is what you wanted to say, right? And Basant. Yes, that's correct, Pooja. So what we mean is, in her words, the drives are connected to the systems which are connected to the network, and we have created a common folder which can be accessed from everywhere. And this common folder contains the mappings to other hard disks. So whenever we are writing into drive one, it's going into the network and going into the drive which is connected in the network. Great. Yes. Correct. Thank you, Dia. So yeah. So what else problems do you see here? As per the problem is that when the network data storage is off, we lose the drive. So okay, so in case the drive containing the main folder, in case we lose that, then we lose everything. So we can also create backups, such as we map these drives on all computers, and we tell all the people that in case this main folder is not accessible on this particular machine, you can use it on another machine. Okay, on all 100 machines. Yeah, so that is a quick fix. So what this is definitely the problem. In case one machine goes down, then there is a big problem. What else problem do you see in this? What other problems do you see in this architecture? Yeah, great, great. Keep going. Speed and access. That is Son's answer. Brilliant. Any other? Cost. Good, good. That's Robert. Okay. Pramesh is saying no replication of data. Great. Switching time. That's Abhishek. Good. Excellent. And Dia says that when we want to execute some algorithm on the drives, yes, then it is going to be problem. Yes. Okay. And Pramesh says that so loss of drive lose will result in loss of data. That's correct. So, but generally what we did, the point which I missed here is generally what we did was on each of the machines, we used to set up our RAID, meaning anything you write to drive 1, there'll be another drive next to the drive 1 on the same computer on which the data gets replicated. So we were able to defend against the hard disk loss by using the RAID. Kiran says throwout will be the bottleneck with all. So do you mean throughput, Kiran? Yeah, yeah, you mean that one. So Kiran says that IO throughput will be the bottleneck with all these drives. Great. That's a brilliant question point. All right, so let's go ahead. So you have actually answered all the questions. So yes, first is the failover and backup. Even if we put the RAID is redundant array of what was that I represent for? I forget, keep forgetting. So we what we used to do is in case of hard disk failure, we generally used to put one more drive along with each drive so that in case hard disk failure is there, we could defend against it. But that does not defend against the network loss, computer operating system problems, or computer hardware failure. Okay, so RAID is not really a good solution for backup and failover. Okay, so even if we put RAID, then also the failover and backup, as you all mentioned, is not really covered. Next is in case, since these are folders, right? So we'll have to make an scheme that where will our data go? In case we are storing all the movies, we'll say all the data, all the movies starting with A will put in first drive, and all the movies starting with B will put in second, and so on. And after some time, we'll realize that one computer is heavily loaded, while other is not loaded. So they will not be able to distribute the data uniformly. Next is this the best value for money? We might have already hard disk lying around, and in case we try to use those hard disks, we'll have other problems like too many computers and will not be able to solve it. Too many folders would be there. Next is increasing accessibility, as Kiran was telling and Dia was telling that increasing accessibility would be the big problem. So let's say there's a new movie that has come in and everybody in the network wants to watch that particular movie, and that movie is stored on a particular drive. Now what will happen is everybody is trying to read the data from the same disk, correct? And the disk is a physical hardware, meaning there's a header which moves from one place to another, so all the people are trying to read the data from there, correct? So what would happen is either this machine would crash, or all others will keep waiting till the till one person finishes watching the movie. Okay. Effectively 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 most of the users will not be able to watch the movie at the same time. So that is increasing accessibility problem. Okay, so the IO throughput and increasing accessibility is the same thing here. Next point, which is scaling out. Today we want to store 100 terabyte. Tomorrow we might have to store 50 more terabytes and so on. Okay, is our architecture good enough? So if we add more machines here, then we'll have to update our scheme, and we'll also have to update. We'll have to tell people that now we are moving movies from this machine to that machine and so on. So there's a lot of work involved. There's a lot of work involved in increasing the scaling out. Okay. Okay. So okay. Thank you, Vinod and Nitin. And RAID is yeah, a redundant array of independent disks. Thank you, Nitin. I'll remember this. Yeah. N- yeah, Sean, correct. In case lots of people try to read the data from the same drive, the drive might end up bursting into flames. Okay. Okay. So we have a few more points. Lingley is saying, besides data consolidation and data analysis, does Hadoop provide capability of enterprise dashboard reporting? So that is something you need to do using your classic tools. Hadoop will provide you an ability to convert big data into small data, the usual dashboard kind of data. And that data you can basically push to your usual systems like BI systems, and from there you can prepare the reporting. So as of now, none of the tools that lie under the umbrella of Hadoop provide you the reporting abilities. Okay. Now Pooja's question is, how about storing same number of files in each drive? That way it would distribute uniformly, right? That's correct, Pooja. So we might think of that way, but which files? Again, same number of files is fine, but how would you decide that? Say today you want to watch a particular movie, you would require an index, right? You would require an index, and there has to be some tool which need to keep on distributing files so that all the drives have equal number of files, right? Also, files the movie files vary a lot. If you take a Blu-ray is 80 GB. A normal movie is 1 gigabyte to 6 gigabytes. So that doesn't really solve the problem. So Dia is saying that we can use then distributed disks or cluster. Yeah, that's another way of looking at it. And the problem keeps on getting complex if you try to solve it. So if we try to solve these points which we have raised just now using our usual network attached storage, you will end up building the distributed database what we are going to talk about. So the answer is that for this kind of for catering to all these requirements is actually a pretty difficult thing. Okay, so what people did then, they built basically Google built the Google file system to solve all these issues which we have mentioned just above. Okay, now how is it built? Okay, so now we are getting into the architecture of Hadoop distributed file system. So all these problems which we talked about, you will realize that all of those problems are solved. If not, let's go through the list once we finish the architecture discussion. Okay, now the way HDFS is built, there is one machine which is earmarked or which is designated as name node, or some people also call it admin node, and rest of the machines in the cluster are earmarked for data node. Now the responsibility of name node is acting like an index. So in our problem which we just discussed, main problem was that where to find which movie. Okay, and to even implement what Pooja was suggesting, we'll have to have an index at a central place, right? So any strategy we go for, we need to have an index, and that's what is the name node. Okay, so name node knows which file is where. Name node tells people that which file is where. You go to name node, you ask that, hey, can you give me this file? And name node tells you that it is on that particular data node. Okay, so name node keeps the metadata. Name node presents you a singular file system. It hides the multitude of the structure. Okay, it hides that from the user. It shows you a single file system. Okay, and all of this metadata is in folder name. What is the file size, the file name, and everything outside the file is stored in name node. Anything inside the file, when you added the file, that there is some data inside the file, that data goes into data node. Okay, so metadata is stored on admin node, and admin node stores all of this data in the memory so that the response is really fast. Although the same metadata is also saved onto the disk in case admin node is killed or something happens, the metadata is in the disk. Now the data nodes are basically for storing the actual data. Okay, so also please keep in mind that these are processes, these are services. And what is a service? When we talk about computing in a network service, a network service is something which keeps running, listening on a port and answering to you. The way a web server responds to your website request, whenever you are asking for a website, a web server is responding with the content in the similar manner. So web server is running on generally 80 port, and similarly these other services are running. Admin service is running on particular port. It's not a physical hardware. Okay, it's just a machine. So this is these are the roles of admin node. All right. Now let's go ahead. Few more things here, and then I'll answer your questions. All right. So the next thing you need to know is that the file, the actual data is sliced into the blocks. So data nodes do not store the files as is. They store the sections of the data. So a big file is broken down into blocks, and by default the size of blocks is 128 MB. The size is flexible, you can change it. Okay, but we will, for the discussion sake, we'll say 128 MB because that's easier to say. So each block is of 128 MB size, and that helps us fitting the big file into smaller disks. Also, it leaves less unused space on the disk. It optimizes the data transfer when we are scaling out. In case one machine is going down, these blocks will get transferred, and it distributes the load into multiple machines. Okay, we will talk about how does it distribute the load into multiple machines by this part. So we have admin node, we have multitude of data node. All the information about which file is where is on the admin node, and these data nodes are storing the actual data in the form of blocks of 128 MB. So if we have 500 MB file, how many blocks are going to be there? Anybody? If we have 500 MB file, they are going to be, let me also compute. Let me open the calculator. So if we have 500 MB file, it is going to be divided into 128 MB pieces, which means there are going to be 4 blocks. 4 into 128 MB is 512 MB, right? Which means the fourth block will be smaller. And how smaller would it be? So you can see. So out of 512, first 3 blocks will consume how much? First block 128 MB minus 128 MB, then 128 MB. Okay, so 500 minus 128 MB minus 128 MB minus 128 MB. So last block will not be of 128 MB. Last block will be of 116 MB. All right. Okay. All right. So let me just repeat it again. Repeat it once more. So HDFS is built with two kind of systems. There is a one machine which is earmarked as admin node, and there are multiple machines which are designated as data nodes. Admin node stores the information that what are the folder names, what is subfolder names, and under those folder names, what is the file name, and the actual data is stored on data nodes. And actual data or actual files are broken down into blocks such that these blocks are movable, as in one block can exist on one data node, other block will exist on another one, and so on. Now, a file is broken down into multiple blocks, and this information that which file is having what all blocks and where all it is stored, our name node or admin node knows it well. All right. Now, next is that each block is replicated, each block is copied, and by default, the replication factor, meaning how many copies are created, is 3. Okay, so by default, each block is copied thrice. Okay, which effectively means that to store 500 MB file, we are going to utilize 1500 MB. Okay, we are going to use 1500 MB storage. So this sounds like waste, but the truth is that when you are dealing with a serious data, you need to have multiple copies. Also, HDFS does not make it mandatory to have these much replication. You can reduce the replication factor to 1, but it's at your own risk. In case one block of a file is lost, the whole file is lost, correct? Even one byte of a file is lost, that means your data is lost. And therefore, you need to have a good replication factor in order to have a good backup. Okay, so therefore, the default one that is chosen is 3. Okay, but if you are using a really sophisticated drive such as solid state drives, you can reduce this replication factor to 2. Okay, because there the reliability is more, but the drives are costly, so replication factor for SSD I generally choose to be 2. Okay, but it is completely up to you how much value you give to the data. All right. And also please note that the backup copies of each block are going to be on another machine. It does not make sense to keep the backup of a data on the same machine, because that will only defend against, that will not defend against anything actually. Correct? If hard disk, I mean, it's not going to defend against anything. If you have the backup copy of the data on the same machine, neither it defends against hard disk failures, operating system failures, network failure, i- or any other problems. Okay, so each copy of the, so if there is a file which having a single block, it'll have two more copies of that particular block, and those two copies are going to be stored in the network. All right, so that was one description. Now I would like to go for the questions now. And okay, now Basant's question is, if same data is distributed in different servers for handling, for handling, say for example, 4 different servers, if 40 users are trying to access it, will first 10 users access it from the first server, next 10, and so on? Yes, that's correct. So if the data is stored in this way, then name node will make sure that the request goes to the backup copies of the data. Okay, and also the blocks will be because the file is broken down into blocks. So imagine you are watching a movie, and this movie is pretty big, say 1 GB, and for 1 GB you will have 8 blocks, correct? So which means 8 users can simultaneously watch this movie if they are having, first one is watching the first block, and second one is watching the second block, and so on. Also, since there is a backup copy of each block, other users can also watch it from the backup copy. Okay, from the copies of the block, from the replicated blocks. All right, so Ingoba's question is that what would happen if name node crash? Yes, very good question. What if this name node, what we see here, it crashes? So whenever we are going into the production, what we do is we keep something called a backup node. So admin node is very highly available, and is also the copy of the data at admin node is also maintained in the backup copy. Whenever data node is informing a name node about anything, it also informs the backup copy. Okay, so we always have a backup name node ready to take the place of admin node. Okay, in high availability settings. So anytime name node goes down, the load immediately shifts to the backup name node. Okay. All right. Did I miss more questions? Yeah. Now, Abhishek's question is there any criteria for choosing which machine becomes admin node? So as we talked earlier that it's a good question. As we talked earlier that name node has basically has data in the memory, which means you should generally have the name node with the big memory. Okay. So generally the node which contains a lot of RAM is what is you designate as name node. Okay. Wow, these are good questions. So Basan's question is there any other pattern followed while splitting the data into blocks? No. So sequentially we keep on slicing the data from we start from one end, measure it 128 MB, slice it, put it in one node, then another block, and so on. So that's a straightforward HDFS dumb way of slicing the data. There's no other way. Ingobar's question is what is the limit on the number of data nodes? So that limit is something which I don't know or they haven't experimented, but if there are beyond a million data nodes, then I don't think they have tested that. Now, if files are stored as multiple blocks in different nodes, if files are stored as multiple blocks in different nodes, then would it not be difficult if one has to access the whole file? That's good question, Pooja. So the way it happens is you do not access these files by yourself. Instead, you use something called a client library, a client, a command line, which will programmatically join this data for you. Okay. And also, in not all circumstances, we want all whole file. So if you want to access programmatically only blocks of data, as the way we watch YouTube videos, right? So when you are watching the first few minutes, it will only hit one data block. When you access the another few minutes, then it will hit another data blocks, and so on. Okay, so you generally don't want the whole data. In those cases, you write the custom drivers to read the data directly from HDFS rather than reading the whole file. All right. Lingley's question is Lingley's question is that so in the situation of using AWS, do we put the copies in different AWS instances? So generally when using HDFS, we do not store the data in AWS or any other virtual systems. Reason being HDFS has been optimized and all the assumptions that are made in design of HDFS is that the data on each data node is stored locally. You will understand it more when we talk about data locality optimizations and other details. Okay, so the way we always designing HDFS, we always make sure that we are talking about we are storing the data on the local drive. Okay, so Vikas, I think I have answered your question. What if name node crashes? Yes. So we'll discuss Kirti that part also about how the blocks are replicated across the network. Okay. So his question is Kirti's question is how the data replication is distributed means if you have multiple machines in the network and the way we design a data center is first we create an Almira. We call this Almira as your rack in which we put multiple computers and then we put multiple Almiras or multiple racks in a data center, right? And each rack is sort of a subnet, is sort of a intranet, and they are because each rack is connected via hub, meaning all the computers on a rack are connected via hub, and these hubs are connected to a router in the data center. So the way data center is architected is that in a data center you have multiple sub networks. So if you have such kind of data center and you have so many thousands of nodes, how does the replication happen? When we have a block, we said that each block is copied multiple times in the network. So where will the other two copies go? And we also said that other two copies will definitely not be on the local machine. Okay. So the way it happens is that first, there are two extremes. One is that if we try to keep the data other two copies really, really far, what would happen is in case this local machine is down, then to access the data, it will take a lot of time. If we keep the other copies very, very close, what would happen is in case there is a fire in the data center, in one data center, then all three copies will get lost. Okay. So there are multiple experiments which SDFS guys have done to to figure out a way to cater to both kinds of extremes. First extreme was keep all the three copies on the same rack. Okay, if not on the same computer. In that case, if there is a fire, all three copies will get lost. Second, second extreme is we keep all these three copies really very, very far. What would happen in that case is, in case one copy is not available, accessing the other copy will take a lot of time, and that will cause a lot of problem. Okay, so the approach has been changed a couple of times. One of the approaches which works right now is when you copy a file to SDFS, the first node should be very close by to the node from which the data is being copied. Okay, if you are copying the data locally from the same machine to the HDFS data node, then first copy will go onto the same machine, second copy will be on the same rack, and third copy will be off the rack and probably in another data center if available. Okay, but this algorithm is very keep on changing. Okay, all right. Wow, this is a lot of questions, and I think I need to first catch up on the questions. So do we have more? All right, the other question is that this replication factor, which is decided as 3, does it increase or auto scale? Say there are 50 people want to watch the same movie. If we increase this replication factor from 3 to something else, that could be great. Okay, but HDFS doesn't do it by default. But there are third-party vendors which provide you this auto scale feature, such as Qbol. Qbol has built their own this kind of auto scale feature. Now, Basant's question is if all right. So Vinayak, could you repeat your question? In that case, what about dirty reads? All right. So yeah. So Basant's question is if one of the data node fails, will it automatically replicate the data in the new node as soon as possible? Yes. So that's what I was about to explain. So if one node fails, all the blocks on that particular data node have disappeared. Correct? Now, which means there are for each block that we have lost, there is other copy still left in the network. So immediately HDFS will automatically create the copies of these blocks so that their replication factor again becomes 3, because the moment data node is lost, all the block that got lost, their replication factor decreased by 1, and therefore it has to be brought again back to the same factor. And that will immediately happen as soon as the data node fails. Okay. So Vinayak, is it possible for you to basically consolidate your question? I am actually a little out of sync, and your question is related to syncing. Yeah. Okay, so Basant's question is, if the failed node is restored, will the replication be automatically handled? Yes. It is very well assumed in HDFS that in case you are restoring a failed node, then all of this synchronization, desynchronization, deletion of the old block and merging of the new block, they all happens very, very quickly. All right. So Lingly, we do not use generally. I do not recommend using HDFS on AWS. AWS provides their own file system. You can use that. Okay. But if you are forced to do it, then you can do that. There's no problem. Okay. And HDFS does its own copying mechanism, no matter what it is. All right. So what is the okay? Ingoba's question is, what is the limit on the number of data nodes? And I don't know exactly how much. What's the limit? Is fragmentation a problem in this architecture? No. That was Abhishek's question. So, is a fragmentation a problem in this architecture? No. Reason being, we are not. This file system is append only, which means in case you are modifying a file, the blocks which are invalid, they will be removed, and it will be as if you have created a fresh new file. So fragmentation is not generally part of the problem. HDFS is exactly a RAID architecture. Okay, I don't know about RAID 3, but I'll definitely like to look at it. All right. So Revan's question is, if my block is 64 MB and my file size is 60 MB, is that mean that 4 MB is wasted? So, okay, so if block size is greater than your file size, it does not mean that there'll be padding or it will take more space. No. If your block size is 64 and your file is 60 MB, there'll be a single block of 60 MB, not 64 MB. Okay, it will not use extra padding or anything, because in case of databases we used to have something called padding so that it takes more space than actually required. That is similar to the physical drive also. All right. Son's question is the data duplicated before storage? No. So as soon as you copy the data, the duplication starts parallelly. As you are writing the blocks into one machine, the blocks are getting concurrently updated, but the confirmation is sent to the user as soon as first copy has finished. Is there any criteria, that is Vikas's question, is there any criteria on which data node the the backup resides? Okay, so as I gave you an example, I think that could have sufficed. So generally first copy is on the node which is closer to the user, second copy is on the same rack, and third copy is on different rack. If the cluster keeps growing and we add more data nodes, is there always one admin node? Yes. One admin node, the reason why we have one admin node is so that there is a single authority on the files, so that there is no inconsistency of the data. So HDFS chooses to have a single node as the master instead of having multiple nodes. So it has chosen the consistency over the availability. We'll talk about consistency and availability when we talk about CAP theorem. All right. Now Basant's question is there any relationship between number of name node and number of data node? No. Name node will always remain one. Ingoba's question is how do we decide the size of name node and data node? It depends on the data you are going to store. Generally, name node in case of production settings, you can start with say 16 GB memory and then you can keep on scaling up as in when your budget is allowed. Okay, so Amish's question is good. He's asking that so whenever the request for a file comes, so will it always be sequential? Will we first read the first block, then read the second block, and then read the third block? How does it happen? So probably I'll answer this question. In case I'm not able to answer, then ping me again. So it is all depends on which client are you using. Okay, and you will understand it more when we understand how the data access happens. Yes, Krishna, we will share the recordings of this session to all the attendees. All right, along with the presentation. Okay. Bhuvneshwar's question is, does all data have a similar architecture? Does all data nodes have similar architecture? So yes, it's the same process, basically same code which is running on data node. If you mean to say whether data node have to be Intel or all have to be AMD or all have to have same OS, the answer is no. As long as each data node is running the same version of Hadoop process, Hadoop is good enough. Hadoop is okay. All right. Nitin's point is may lead to inconsistencies, not seamless user experience. I missed which point are we talking about? So, okay. So Kirti's question is, can the admin take a decision in the distribution, maybe in the config file, or it's automatically handled by Java program? So it's basically handled by the strategy, which is generally part of the main code. Okay. And I'm not sure if they have provided any knob or any control switch on shifting between multiple strategies. Okay. I have not yet encountered a scenario where we had to customize the strategy for the distribution. Okay, okay. Now Vinayak's question is that when multiple copies of a file are accessed simultaneously, how are dirty reads handled? Okay, so Vinayak's question basically is if if the data is getting written and some user is reading it, how is dirty read handled? Okay, so generally, HDFS does not allow you reading the data until the data has finished committing. It does not allow the dirty reads. All right. In a commercial implementation of Hadoop, what is the basic setup? Setup looks like how many nodes? Okay. So generally the nodes at least have to be four. Okay. Even in the smallest possible setup of Hadoop, there has to be at least 4 nodes. Although there are virtual machines containing data node on name node on the same machine, but it doesn't make any sense. Okay, so the smallest number of nodes that you require to have the smallest setup is four nodes, and rest is up to your requirement, Anura. You want to have thousands of nodes, you can do that. So when we were at InMobi, we just bought around 10 computers and started our HDFS. Okay, we bought these 10 computers from those people who sell the normal average computers, and we set it up using the off the shelf hardware. And we started with 10 nodes, and it did pretty well. Okay. So Sandhya's question is, what if you accidentally delete the data? Will it be possible to retrieve it? Okay. So the answer to this is no. If you delete the data, it will not be possible to retrieve it. The only thing which HDFS provides against this is when you delete a data, the client library is provided that is provided to you. It moves the data to trash. It moves the data to trash folder, and then you can recover it later point of time. Okay, there's the only defense they have. There is no though in case of HBase, it maintains versions of the data. In the HBase is the database on top of Hadoop. All right, it maintains the versions of the data, and there you can recover the lost copies. Okay, so Dia's question is, can we use many clusters, and how can we synchronize all of them? Meaning, do you want to set up multiple different cluster, as in one cluster containing its own admin node and data node and so on, then another cluster containing name node and data node and so on? Is that what you mean? Oh, yeah, that is going to be really difficult question to answer. Yeah. So because what happens is when you have multiple name node and admin node, so multiple the people are creating the files simultaneously. The only way to synchronize these files is by the way of creation timestamp. Okay, and so there is no straight way to do this. Okay, there is no such thing called versioning, and because using versions, people generally are able to synchronize the file systems. Because if you try to synchronize two or more different file systems together, there are chance of there is a lot of chance of conflict. Okay, although you could use tools like the dist copy, which is provided by Hadoop, to do this, but not really advised. Okay, and generally the way HDFS has been designed, there is a singular file system in the whole organization. Always we keep a singular file system in the whole organization, a single HDFS, which we give different people different set of permissions so that they can only manipulate some part of data rather than all manipulating everything. Okay, so Nitin's question is, yeah, actually I'll have to consolidate your questions. Your first point was may lead to inconsistent, not seamless user experience, data nodes too far, low latency data access, lots of small files, multiple writers, arbitrary file modifications. So what exactly is your question? So how does HDFS, now I get it. How does HDFS solves these problems such as low latency data access. Okay, so basically I'll show you those all. Don't worry. Now probably, okay, okay. Yeah, Dia's question is further to that. So the further question is that so we can just add nodes. Yes, we can just keep on adding nodes, and these blocks will keep on moving and redistributing itself to the network. All right. So you don't have to worry about the scalability at all. You can keep on adding data nodes, and that's all. You add the data node, tell the data node where is admin node, and tell admin node this is your new data node, and that's all. Okay. All right. Now question back to Nitin. So let me explain one more slide and then I'll take the question by Nitin. All right. All right. So when you have a user uh, and there is name node and data node, the impression which people get is that name node will become the bottleneck, right? User will come to name node will read data from all the data nodes and give it back to the user, but that is not the case. Instead, clients ask the name node that give me the data, and name node, instead of giving the data, tells the client that these are the 5 blocks located on these 5 different machines. Go to the node whichever is closer to you and read from there. It's as simple as that. And now client driver will go directly to the data node and start reading from there instead of waiting for name node to give the data. Okay, that way name node frees itself. Name node does not become the bottleneck. Name node makes itself free from the from the whole latency. Okay, so otherwise what would happen is name node will become the bottleneck, since everybody all of the data is going through name node. Okay, therefore all the data reads and writes directly happen on the data nodes. Name node just acts as a accountant. It just does the accountancy of the files, that this file has got this many blocks, these blocks have to go on these nodes, and so on. That way now you can understand, Nitin, that SDFS solves the low latency data access this way. Now, your next question was, what if there are a lot of small files? So, yes, that's a big challenge. So, imagine that you have 1 MB files, okay? Which means you have 1 TB of data with where there are 1 million files, each of 1 MB, okay? Now, what would happen is that there will be 1 million blocks, and therefore there will be too much of metadata, and in turn what will happen is, since there is too much of metadata, what would happen is name node will become full. Okay, if for each file name node is dedicating a small amount of metadata memory of say 1 KB, still the 1 GB of memory will go into maintaining this kind of metadata, correct? And therefore small files are not really greatly handled by HDFS. There are other formats. So what we generally do is, when we have a lot of small files, we basically create something called tar or something called a zip file, which is easier to handle. So we'll talk about, there is one kind of format, RC format for example, where we create splittable zip files which can be divided onto the network. All right. Now, next question was, what if there are multiple writers? Okay, so what if there are multiple writers? These are very good questions. What if there are multiple people trying to create to the same file? Now, since there is a single name node ensures that there is always a consistency. And name node makes sure that only one writer writes to the file at a single time. Okay, because it prefers strong consistency over high availability. Now, next problem with the next question from Nitin Patel is, what happens in case of arbitrary file modification? So HDFS does not allow you to do the arbitrary file modification. File modification is equivalent of deleting the old file and creating a new file. Therefore, HDFS is generally called append only file system. All right. I hope that answers your questions. So Manikandan, can you just drop me an email at reach us at no big data, then we can discuss it over email. All right. Anirudh's question is that what is the capacity of name node? Okay. So it all depends on your budget and how do you want to structure your name node. But generally, you keep a little higher memory on the name node. Okay. Amish's question is that does metadata in name node supposed to be held in the memory to make it efficient? Yes, correct. So yes, so the metadata in name node is supposed to be held in the memory, and that's how name node works. So that it immediately is able to answer the question asked by you rather than reading the data from the disk and then answering. All right. All right, so we have Anirudh's question. Hadoop is about reading the data or inserting and updating the existing data by thousands of users. Not really, not really. There are many different kind of scenarios for which these file systems are great. Okay, so even if you have no existing reading, no data is being read from the HDFS, but there might be terabytes of data lying around, and there is this program which need to be run on top of data. So for example, I was handling a few hundred terabytes of data. I was actually handling 200 terabyte of data at InMobi. So what we were doing is this data was lying in the HDFS, and my program is supposed to go through this data, clean it, and then prepare a uh, prepare the data which will be fed to Mahout, the 3 column data. Okay. So for this kind of analysis, even if there are no multiple users and nothing, there's only one program that needs to do this. Still, since the data is huge, running it single node will take forever. Okay. So to handle these kind of scenarios, we can use this. All right. So there are many use cases where the name node and HDFS works. All right. So again, I will quickly go through the flow again. Anirudh's question is how concurrent inserts are handled by common data node. So concurrent is not allowed. So name node maintains the queue and name node maintains the concurrency. Okay. So only one writer is allowed at one time, and readers as well as other writers are wait till one writer finishes. All right. All right. So yeah. So Nitin, yeah, that's what I've been telling. That the way Hadoop's architecture has been designed is it's a write ahead, means you keep on writing the data to append only, and then you basically read afterwards. All right. So okay, let me get back to this slide. So first, let me describe what is a rack. A rack is an almirah, or you can think of rack as collection of computers, and these computers are connected together to a single hub. So if you have three racks, which means three hubs, and these three hubs will be connected to a router. Okay. So each rack itself is basically a network, and that network gets connected to other racks via a common router. All right. So in this diagram, what we show is that there is one rack containing one node, two node, three node. These are three different data nodes. There is rack 2 containing data two data nodes, and each of the data node is containing multiple blocks from different files, not from the same file, but from different files, or maybe from the same file. Okay, and replication is happening between these data from one rack to another. Okay, so a client comes in to read the data. It goes to metadata and asks for the file location. Then it basically reads the data from each individual machines and then serves to its customer. Similarly, another client comes in to write the data. First, it goes to the name node, informs that, hey, I'm planning to write this particular file, so block all the access on this file. And then client starts writing the data. And once it finishes writing the data, it goes back to the name node and informs that, hey, I'm done with writing the data. Okay. But the write and read both happen directly on the data nodes. All right. Now it makes sense to you, Dia? All right. So that's pretty much about HDFS architecture. All right. So yeah, let me describe other components and then we can take further questions. All right. Now we discussed something called HDFS. We will discuss all these components during these 11 sessions in detail. And other than these components, we will discuss one more component called Zookeeper. All right. So on the top of HDFS, when you have to import the data from unstructured sources such as Apache web servers or your continuously generated logs or something else, in those cases you use Flume. All right. And in case you want to transfer the data from your RDBMS, which means relational database, you can use Scoop to transfer the data. Basically, Flume and Scoop both are heavily distributed and you can copy the data. Okay. Now, after this, you have something called Yarn. Yarn is, you can think of, is a network kind of an operating system to which we ask that, can you execute this program, and it execute that program on any of the nodes available. So Yarn is a compute engine which makes it possible to execute a program parallelly on multiple nodes. And Yarn acts as the operating system for other components such as MapReduce. So MapReduce is basically framework using which you break down your whole problem statement into sequences of maps and reduces and feed it the map program and reduce program which gets executed. Map is a function which you create and reduce is also another function which you create, and you get it executed over multitude of blocks, and whatever is the result, you pass it through your reduce function and you return the results. We will go into the details of MapReduce. In case you are utterly confused, do not worry. Okay, right now it's difficult right now to explain in detail, but we'll discuss it tomorrow. All right. Then we have Spark. Spark is also a programming paradigm like MapReduce, but really fast one, which utilizes a lot of memory. And we will compare when to use MapReduce and when to use Spark. And in session 8 or 9, we'll go into the details of Spark. If you have to do record-wise deletion, updation, or record-wise manipulation of the data, then you use HBase. Okay. In other words, if your data involves a lot of modification, then you use HBase. And but HBase does not provide you any query language. So for that, you use Hive. Using Hive, you can query the data that is lying in HBase or that is lying in HDFS. Okay. Now, similar to Hive, we have Pig-Latin. Pig-Latin is very similar to our usual SQL, but But Pig-Latin is designed from bottom up, keeping in mind the performance. Okay, because our usual SQL, which is used in Hive, is not designed for distributed computing. Okay, but Pig-Latin, the way it is designed, is heavily optimized for distributed computing. Then we have Mahout. Mahout is basically a collection of various algorithms which run distributively on multiple computers. And since we have all these components, and whenever you are building anything, you will utilize at least 2 to 3 components from the ecosystem. And to tie them together, you generally use a workflow like Oozie, similar to Maven or Ant script. Maven or Ant script, you use Oozie workflow. All right. And you can interact with Hadoop either from command line or using Java program or using Python or using a web interface. All right. So that's pretty much about the ecosystem. There are 2 more questions. So Anirudh's question is, all these components belong to one data node? No. Okay. The data node and name node is only part of Hadoop distributed file system. So on the same machines on which we are running data node, we might install yarn also on those, and Hive, Pig, and these things are command line libraries, which means that you don't need to run Pig and Hive parallelly on any machine. They are client libraries. So basically you have machines on which some machines you will dedicate to data nodes. One machine you will earmark for name node. On the same machines, you will also install Oozie, Pig, Hive, HBase. So HBase also has components like master and slaves. Similarly, in case of MapReduce, you also have master and slaves. You will install these master and slaves parallelly. All right. So I will show you this part. Yes, Manikandan. Yarn is Hadoop 2.0. That is correct. So Basant's question is, does Flume and Scoop handles the file distribution differently? No. So Flume basically copies the data to HDFS at really fast pace, while Scoop helps you querying any MySQL or Oracle or Microsoft SQL and put the data into the network. All right. So that was pretty much. Now, some of us would be having questions related to Cloud Labs. Okay. And we will discuss more about Cloud Labs. So right now, I'll just show you. So this is our Ambari. Ambari is our provisioning software using which we control our cluster. Okay. So yeah, so you can see that it has got HDFS. HDFS has got data nodes. We have got 4 data nodes, and these data nodes are stored on Hadoop 1, 2, 3, 4, and these are 4 machines which we have dedicated for this. And also note that on Hadoop 1, name node is stored on Hadoop 1. Okay, and on Hadoop 1, these are the other services that are running. You can see that. Okay, Anirudh, does that answer your question? On Hadoop 1 is one machine. On Hadoop 1, both data node and name node I'm running right now, although it's not a good pattern, but I've just run it for the sake of it. Okay. All right. All right. So this is a quick one. So what we have done is we have basically have 4 hosts, and on each host we have installed these multiple components, and you can connect to these either from browser. We'll show you how to connect to this. So this is how your HDFS generally looks like. So given the data node, name node, you might be wondering that is it really a file system or is it something else? So this should answer your question. Now look at this. This is basically our HDFS. You can see that these are our files from different students, and this is the data. Okay, and we have say all of this data is basically in our HDFS cluster. Okay, sounds good to you? All right, all right. So this is basically Cloud Labs. The way we work in any organization is not on the virtual machine, but on a centrally dedicated cluster on which we basically put our files and do our all processing. In the similar way, we have set up Cloud Labs. Okay, so you can directly connect to Cloud Labs Unix by from the command line. You can say SSH, and you can connect. Okay. So password would be shared with you in the installation guide. You can look at that. All right. Oh, sorry. We have to mention that. All right. So you can go through it, and if you have to say the same thing in HDFS, we'll say Hadoop fs minus ls. It will give the listing of all the files in HDFS. Okay. Same way we did on the website. Okay, so that was pretty much about the HDFS. Those who want to sign up for the full course, they can sign up, and here are the works. Those who have attended today's session, please go through the exercise given in the LMS. Okay, also try to install Putty if you're on Windows. If you're on Mac or Ubuntu, you don't have to do anything. You just the SSH client is already there, but for Windows you have to install SSH client, that is Putty. Okay, also finish the quiz given in LMS, and see the assignment section in LMS. All right. And for further details, you go through these. You might want to go for these readings, further reading. And those who want to sign up for the full course, almost this session is almost full. The one which is started today, it's almost full. Okay. So yeah, you can, but still there are few seats, two or three seats left only, and you can sign up for that. Okay. All right, so thank you very much and stay in touch. Okay, see you tomorrow at the same time. Thank you, Anirudh. Thank you, Amish. Thank you, Basant. Thank you, Kirti. Thank you, Dia. See you tomorrow. Thank you, Kiran. Thank you, Ingoba. I am happy that you liked the session. And yeah, Aruna, what's your question? So, what is the full course? So, full course will include all these components. We'll study all these components in detail, how to interact. Okay. All right. Thank you very much. And if you have any questions, feel free to drop me an email or go through our forum. There are a lot of good information over there. And also feel free to ask the question. You can register on the forum and ask the question. Okay. Yes, Nitin. Under my course, you will see the courses which you have taken. Yes, Nitin. It shows that 30 May batch, Saturday, Sunday, 3 hours per session. That's correct. Oh, is it so? Let me see. I did not notice this. Okay. That is actually funny. Yeah. So let me correct this mistake. And so it shows Saturday dash Saturday, right? Uh, but it shows to me Saturday, Sunday. Can you send me the screenshot, Nitin? That will be better because I'm not able to reproduce that. So tomorrow it will be only for the students, Pooja. It will not be an open session. Okay. So assignment, if you go into my courses and you click on 30 May, and there under that you will see the session 1. First you go through the installation instructions for putty and other installation, and then you can take the quiz. Okay, Abhishek? All right. And Nitin, which time zone do you come from? CST. Okay, let me test it in CST because it behaves differently in different CSTs. All right. Okay. So see you tomorrow. Bye bye. Have a good day. Feel free to get in touch if you have any questions.